Chapter 9, Process Specifications and Structured Decisions. Learning Objectives. Once you have mastered the material in this chapter, you will be able to understand the purpose of process specifications. Recognize the difference between structured and semi-structured decisions. Use structured English, decision tables, and decision trees to analyze, describe, and document structured decisions. Choose an appropriate decision analysis method for analyzing structured decisions and creating process specifications. This submitted by Denmark Tagik. Submitted to Engineer Elena Morasieras. Logic of decisions. It is important to recognize logic and structured decisions that occur in a business and how they are different from semi-structured decisions that tend to involve human judgments. It is also critical to recognize that structured decisions lend themselves to analysis with systematic methods. Documenting and analyzing logic. Structured English. Decision tables. Decision trees. Logic and structured decisions are distinguishable from semi-structured decisions. Structured decision analysis methods promote completeness, accuracy, and communication. Major topics of this topic are process specifications, business rule, structured English, decision tables, decision trees, and horizontal balancing. Goals of producing process specifications. This is the three main goals of the producing process specifications. Reduce process ambiguity. Obtain a precise description of what is accomplished. Validate the system design. Reduce process ambiguity, compels the analyst to learn details about how the process works. Obtain a precise description of what is accomplished, usually included in a packet of specifications for the programmer. Validate the system design, ensures that a process has all the input data flow necessary for producing the output. Process specifications are not created. Process specifications are not created for processes requiring physical input or output, processes representing simple data validation, or processes with pre-existing and pre-written code. Processes that represent physical input and/or output. Processes that represent simple data validation. Processes that use pre-written code. Sometimes the process is very simple or the computer code already exists. In these cases, process specifications are not created. Processes that use pre-written code. These processes are generally included in a system as subprograms and functions. Process specifications, sometimes called mini-specs. Created for primitive processes as well as for some higher-level processes on a data flow diagram. Created for class methods in object-oriented design and for the steps in a use case. Process specification is a method used to document, analyze, and explain the decision-making logic and formulas used to create output data from process input data. Its objective is to flow down and specify regulatory/engineering requirements and procedures. Called mini-specs because they are a small portion of the total product specifications. Specifications explain the decision-making logic and formulas that transform process input data into output. These are the 9 process specification format you need to remember: the process number, the process name, description of what the process accomplishes, a list of input data flow, output data flows, type of process, uses pre-written code, process logic description, logic method reference, list any unresolved issues. Process specifications link the process to the data flow diagram, and hence the data dictionary. Each process specification should be entered on a separate form or into a case tool screen such as the one used for Visible Analyst and shown in the CPU case at the end of this chapter. Enter the following information. 1. The process number, which must match the process ID on the data flow diagram. This specification allows an analyst to work on or review any process, and to locate the data flow diagram containing the process easily. 2. The process name, which again must be the same as the name displayed in the process symbol on the data flow diagram. 3. A brief description of what the process accomplishes. 4. A list of input data flows, using the names found on the data flow diagram. Data names used in the formula or logic should match those in the data dictionary to ensure consistency and good communication. 5. The output data flows, also using data flow diagram and data dictionary names. 6. An indication of the type of process, batch, online, or manual. All online processes require screen designs, and all manual processes should have well-defined procedures for employees performing the process tasks. 7. If the process uses pre-written code, include the name of the subprogram or function containing that code. 8. A description of the process logic that states policy and business rules in everyday language, not computer language pseudocode. Business rules are the procedures, or perhaps a set of conditions or formulas, that allow a corporation to run its business. The early problem definition, as explained in Chapter 3, that you completed initially may provide a starting place for this description. Common business rule formats include the following. Definitions of business terms. Business conditions and actions. Data integrity constraints. Mathematical and functional derivations. Logical inferences. Processing sequences. Relationships among facts about the business. 9. If there is not enough room on the form for a complete structured English description, or if there is a decision table or tree depicting the logic, include the corresponding table or tree name. 10. List any unresolved issues, incomplete portions of logic, or other concerns. These issues form the basis of the questions used for follow-up interviews with users or business experts you have added to your project team. These items should be entered to complete a process specification form, which includes a process number, process name, or both from the data flow diagram, as well as the 8 other items shown in the world's trend example, figure 9.2. Notice that completing this form thoroughly facilitates linking the process to the data flow diagram and the data dictionary. Just remember this in process specification. The process number. The process name. Description of what the process accomplishes. A list of input data flow. Output data flows. Type of process. Uses pre-written code. Process logic description. Logic method reference. List any unresolved issues. Figure 9.1 How process specifications relate to the data flow diagram. Process specifications link the process to the DFD and the data dictionary. Business rule. A business rule defines or constrains some aspect of business and always resolves to either true or false. For example, a business rule might state that no credit check is to be performed on return customers. Definitions of business terms. Business conditions and actions. Data integrity constraints. Mathematical and functional derivations. Logical inferences. Processing sequences. Relationships among facts about the business. Structure English. When the process logic involves formulas or iteration, or when structured decisions are not complex, an appropriate technique for analyzing the decision process is the use of structured English. As the name implies, structured English is based on 1. Structured logic, or instructions organized into nested and grouped procedures, and 2. Simple English statements such as add, multiply, and move. A word problem can be transformed into structured English by putting the decision rules into their proper sequence and using the convention of if-then-else statements throughout. Writing structured English. Underline words or phrases that have been defined in a data dictionary to signify that they have a specialized, reserved meaning. Be careful when using and or. Avoid confusion when using logical comparisons such as greater than and greater than or equal to and like relations. Clarify the logical statements now rather than waiting until the program coding stage. Take note. Express all logic in terms of sequential structures, decision structures, case structures, or iterations. Use and capitalize accepted keywords such as if, then, else, do, and perform. Indent blocks of statements to show their hierarchy, nesting, clearly. Underline words or phrases that have been defined in a data dictionary. Clarify the logical statements. Figure 9.2. An example of a completed process specification form for determining whether an item is available. Completing this form facilitates linking process to the data flow diagram and the data dictionary. As you can see in the figure 9.3, this is the example of logic expressed in a sequential structure, a decision structure, a case structure, and an iteration. You can use and capitalize accepted keywords such as if, then, else, do, and perform. Advantages of structured English. Clarifying the logic and relationships found in human languages. An effective communication tool, it can be taught to and understood by users in the organization. Data dictionary and process specifications. In figure 9.6, you will able to see the example way how to write in structure English. The data dictionary is a starting point for creating structured English. Sequence, a simple sequence of statements move, add, and subtract. Selection, entries become if then, else statements. Iteration entries become do while, do until, or perform until. All computer programs may be coded using the three basic constructs, sequence, selection, and iteration. The data dictionary indicates which of these constructs must be included in the process specifications. Decision table. A table of rows and columns, separated into 4 quadrants. Conditions. Condition alternatives. Actions to be taken. Rules for executing the actions. In decision table. As shown in figure 9.7. The upper left quadrant contains the condition, S, the upper right quadrant contains the condition alternatives. The lower half of the table contains the actions to be taken on the left and the rules for executing the actions on the right. When a decision table is used to determine which action needs to be taken, the logic moves clockwise beginning from the upper left. Suppose a store wanted to illustrate its policy on non-cash customer purchases. The company could do so using a simple decision table as shown in figure 9.8. Each of the 3 conditions, sale under $50, pays by check, and uses credit cards, has only 2 alternatives. The 2 alternatives are Y, yes, it is true, or N, no, it is not true. 4 actions are possible. Complete the sale after verifying the signature. Complete the sale. No signature needed. Call the supervisor for approval. Communicate electronically with the bank for credit card authorization. A decision table is a table of rows and columns, separated into 4 quadrants. The upper left quadrant contains the conditions. The upper right quadrant contains the condition alternatives. The lower half of the table contains the actions to be taken on the left and the rules for executing the actions on the right. When a decision table is used to determine which action needs to be taken, the logic moves clockwise beginning from the upper left. Developing decision tables. To build decision tables, the analyst needs to determine the maximum size of the table, eliminate any impossible situations, inconsistencies, or redundancies, and simplify the table as much as possible. The following steps provide the analyst with a systematic method for developing decision tables. Determine the number of conditions that may affect the decision. Combine rows that overlap, such as conditions that are mutually exclusive. The number of conditions becomes the number of rows in the top half of the decision table. Determine the number of possible actions that can be taken. That number becomes the number of rows in the lower half of the decision table. Determine the number of condition alternatives for each condition. In the simplest form of decision table, there would be 2 alternatives, Y or N, for each condition. In an extended entry table, there may be many alternatives for each condition. Make sure that all possible values for the condition are included. For example, if a problem statement calculating a customer discount mentions one range of values for an order total from $100 to $1,000 and another range of greater than $1,000, The analyst should realize that the range from $0 up to $100 should also be added as a condition. This is especially true when there are other conditions that may apply to the $0 up to $100 order total. 4. Calculate the maximum number of columns in the decision table by multiplying the number of alternatives for each condition. If there were 4 conditions and 2 alternatives, y or n, for each of the conditions, there would be 16 possibilities as follows. Condition 1, times 2 alternatives. Condition 2, times 2 alternatives. Condition 3, times 2 alternatives. Condition 4, times 2 alternatives. 16 possibilities. 5. Fill in the condition alternatives. Start with the first condition and divide the number of columns by the number of alternatives for that condition. In the foregoing example, there are 16 columns and 2 alternatives, y or n, so 16 divided by 2 is 8. Then choose one of the alternatives, say y, and write it in the first 8 columns. Finish by writing n in the remaining 8 columns as follows. Condition 1, y y y y y y y y n n n n n n n n. Repeat this step for each condition, using a subset of the table. Condition 1, y y y y y y y y n n n n n n n n. Condition 2, y y y y n n n n. Condition 3, y y n n. Condition 4, y n. And continue the pattern for each condition. Condition 1, y y y y y y y y n n n n n n n n. Condition 2, y y y y n n n n y y y y n n n n. Condition 3, y y n n y y n n y y n n y y n n. Condition 4, y n y n y n y n y n y n y n y n. 6. Complete the table by inserting an X where rule suggests certain actions. 7. Combine rules where it is apparent that an alternative does not make a difference in the outcome. For example, can be expressed as Condition 1, yy. Condition 2, yn. Action 1, xx. Condition 1, y. Condition 2. Action 1, x. The dash signifies that condition 2 can be either y or n, and the action will still be taken. 8. Check the table for any impossible situations, contradictions, and redundancies. They are discussed in more detail later. 9. Rearrange the conditions and actions, or even rules, if it makes the decision table more understandable. Decision table processors, which take the decision table as input and provide computer program code as output, are available. Figure 9.8 Constructing a decision table for deciding which catalog to send to customers who order only from selected catalogs. Checking for completeness and accuracy. Incompleteness: if a condition is left out, the whole decision table would change because a new condition, new set of alternatives, new action, and one or more new action rules would have to be added. Impossible situations: for example, a person cannot earn greater than $50,000 per year and less than $2,000 per month. Contradictions occur when rules suggest different actions but satisfy the same conditions. Redundancy occurs when identical sets of alternatives require the exact same action. Physical and logical process specifications. How can a data flow diagram be transformed into a process specification? Each data flow diagram process expands to a child diagram, a structure chart, or process specification. How process specifications can be used to balance, and correct, a data flow diagram. If the process is primitive, the specifications show the logic, arithmetic, or algorithm for transforming the input into output. Decision table advantages. Decision table processors, which take the decision table as input and provide computer program code as output, are available. Help the analysis ensure completeness. Easy to check for possible errors. Impossible situations. Contradictions. Redundancy. Decision trees. Decision trees are used when complex branching occurs in a structured decision process. Trees are also useful when it is essential to keep a string of decisions in a particular sequence. Although the decision tree derives its name from natural trees, decision trees are most often drawn on their side, with the root of the tree on the left side of the paper. From there, the tree branches out to the right. This orientation allows the analyst to write on the branches to describe conditions and actions. Unlike the decision tree used in management science, the analyst's tree does not contain probabilities and outcomes. In systems analysis, trees are used mainly for identifying and organizing conditions and actions in a completely structured decision process. Figure 9.14 Checking the decision table for inadvertent contradictions and redundancy is important. Decision trees are used when complex branching occurs in a structured decision process. Trees are also useful when it is essential to keep a string of decisions in a particular sequence. Drawing decision trees. It is useful to distinguish between conditions and actions when drawing decision trees. This distinction is especially relevant when conditions and actions take place over a period of time and their sequence is important. For this purpose, use a square node to indicate an action and a circle to represent a condition. Using notation makes the decision tree more readable, as does numbering the circles and squares sequentially. Think of a circle as signifying if, whereas the square means then. When decision tables were discussed in an earlier section, a point of sale example was used to determine the purchase approval actions for a department store. Conditions included the amount of the sale, under $50, and whether the customer paid by check or credit card. The four actions possible were to complete the sale after verifying the signature, complete the sale with no signature needed, call the supervisor for approval, or communicate electronically with the bank for credit card authorization. Figure 9.14 illustrates how this example can be drawn as a decision tree. In drawing the tree, 1. Identify all conditions and actions and their order and timing, if they are critical. 2. Begin building the tree from left to right, making sure you list all possible alternatives before moving to the right. This simple tree is symmetrical, and the four actions at the end are unique. A tree does not need to be symmetrical. Most decision trees have conditions that have a different number of branches. Also, identical actions may appear more than once. A tree does not need to be symmetrical. Most decision trees have conditions that have a different number of branches. Identical actions may appear more than once. More advanced decision tables. As the number of alternatives and conditions grow, the number of columns increases. A table with 7 conditions each having 2 alternatives would need 128 columns. To reduce the number of columns, use extended entries. Use the else rule. Construct multiple tables. Decision trees advantage. It takes advantage of the sequential structure of decision tree branches so that the order of checking conditions and executing actions is immediately noticeable. Conditions and actions of decision trees are found on some branches but not on others. Compared to decision tables, decision trees are more readily understood by others in the organization. Choosing a structured decision analysis technique. We have examined the 3 techniques for analysis of structured decisions: structured English, decision tables, and decision trees. Although they need not be used exclusively, it is customary to choose one analysis technique for a decision rather than employing all 3. The following guidelines provide you with a way to choose one of the 3 techniques for a particular case. Use structured English when there are many repetitious actions, or communication to end users is important. Use decision tables when complex combinations of conditions, actions, and rules are found, or you require a method that effectively avoids impossible situations, redundancies, and contradictions. Use decision trees when the sequence of conditions and actions is critical, or when not every condition is relevant to every action, the branches are different. Selecting a structured decision analysis technique. Use structured English when there are many repetitious actions or when communication to end users is important. Use decision tables when complex combination of conditions, actions, and rules are found or you require a method that effectively avoids impossible situations, redundancies, and contradictions. Use decision trees when the sequence of conditions and actions is critical or when not every condition is relevant to every action, the branches are different. Physical and logical process specifications. If the process is primitive, the specifications show the logic, arithmetic, or algorithm for transforming the input into output. How can a data flow diagram be transformed into a process specification? Each data flow diagram process expands to a child diagram, a structure chart, or process specification. How process specifications can be used to balance, and correct, a data flow diagram. Using process specifications, horizontal balancing. Horizontal balancing machines use of the Schenck-Hard bearing principle, with the middle section of the bearing form the balancing process quickly. Horizontal balancing dictates that all output data flow elements must be obtained from the input elements and process logic. A method where process specifications are used to analyze the data flow diagram and data dictionary. Horizontal balancing rules. All base elements on an output data flow must be present on an input data flow. All derived elements on an output data flow must be either present on an input data flow, or created by the process. Unresolved areas are posted as questions during follow-up interviews with key users. As a systems analyst, the person in the organization most involved with systems analysis shows how to use process specifications for horizontal balancing. Summary. 1. Process specifications. 2. Decision analysis. Structured English. Logic is expressed in sequential structures, decision structures, case structures, or iterations. 3. Decision tables. 4 quadrants are used to describe the conditions. Identify possible decision alternatives. Indicate which actions should be performed. Describe the actions. 4. Decision trees. Consists of nodes and branches. 5. Decision analysis advantages. Structured English is useful when many actions are repeated and when communicating with others is important. Decision tables provide complete analysis of complex situations while limiting the need for change attributable to impossible situations, redundancies, or contradictions. Decision trees are important when proper sequencing of conditions and actions is critical and when each condition is not relevant to each action. 6. Horizontal balancing. Using process specifications to analyze the data flow and data dictionary.